Digital still cameras can capture beautiful high-resolution images. Digital video cameras, on the other hand, are still producing low-resolution video, even with the move to HD. Hybrid cameras that support the simultaneous capture of low-resolution video and high-resolution stills are now becoming available, but they're still limited in their capture capabilities and produce low-quality images. In anticipation of improvements in these cameras, we present a software framework that is able to flow high-resolution information across space and time by combining a few high-resolution stills with a low-resolution video. Since these cameras are not yet available, we use data from two sources. First, we use a two-camera setup by placing an SLR digital camera and a camcorder in close proximity. We use photos from one and video from the other as the hybrid input. Second, we simulate the input data. We start with a high spatial resolution video and downsample it 4 to 8 times to produce a lower spatial resolution video. We use this low resolution video, together with some of the frames from the original video, to simulate the output of a hybrid camera. Where not specified, the results shown in the video are simulated. Our system can provide a variety of spatial and/or temporal resolution enhancements. We can combine a low-resolution video with high-resolution stills to produce a high spatial resolution video. We can also increase the temporal resolution of a video to produce a slow-motion video. We can combine these two steps to first enhance the spatial resolution of a video and then increase the temporal resolution to produce a higher spatiotemporal resolution video. We start with a segment of low-resolution video and two boundary high-resolution stills. We first upsample the low-resolution frames to match the size of the high-resolution stills. To find the motion correspondences between the high and low-resolution frames, we could use a number of different techniques. We could compute optical flow from the high-resolution boundary stills to each of the interval frames. This approach produces errors because of the differences in image resolution. Alternatively, we could use the low-resolution boundary frames instead of the high-resolution ones. This improves matching, but without good initialization, optical flow often fails to find good correspondences between frames that are far apart in time. We could also compute pairwise optical flow and sum the flow vectors to estimate correspondence between distant frames. This approach performs still better, but flow errors tend to accumulate. Our approach is to use the summed flow vectors to initialize a second optical flow stage between the boundary and intermediate frames. Using this method, we compute motion correspondences for the interval in the forward and reverse directions, and then composite the warped boundary frames using a graphical optimization to produce the high-resolution frame. Finally, as described in the paper, a spacetime fusion step combines the composites with temporal constraints from optical flow on the original segment to produce a video that has high spatial resolution and is temporally coherent. Temporal resolution is increased similarly. To generate an intermediate frame, we compute optical flow between adjacent frames and warp them along flow lines to the new frame. A graphical compositing step combines these warped frames. Our framework enables a variety of applications previously unavailable to consumers. In this very challenging example, the low-resolution video lacks all details of the water surface and dolphins. The high-resolution stills capture the details of interest, but do not convey the dynamics of the scene. Let's look at how the 4 optical flow approaches perform on this challenging example. The first approach is to compute flow directly between the high-resolution boundary frames and the low-resolution intermediate frames. This approach produces many artifacts, including ghosting and blurring. The second approach is to compute flow between the lower resolution boundary frames and intermediate frames. This approach does not improve the result significantly because the motion between the boundary and intermediate frames is large. The third approach is to sum up pairwise optical flow between frames and use the sum as a better estimate for the motion between distant frames. This approach performs much better, but does have some artifacts, such as motion trails near the fins, due to error accumulation. Finally, our two-step approach produces a video that is visually consistent and has relatively few artifacts, despite the challenging content. Once we have motion correspondence, we can create high-resolution frames. A standard approach is to do a weighted average of warped frames, also known as morphing. Here, morphing results in many artifacts, such as tearing, near the fins and tails, because the motion correspondence in these regions is inaccurate. Our approach is also sensitive to the quality of optical flow, but it attempts to preserve shapes by making a trade-off between spatial resolution and temporal consistency. Even in this difficult case, we're able to reconstruct water droplets and other surface details. This example is also challenging, but for different reasons. It has low texture variance in the face, a deforming flame, waving hair, facial expressions, and a variety of lighting effects. The optical flow is inaccurate and results in many tearing artifacts for the naive morphing approach. Our approach produces smoother results, but retains the lighting effects. Although it is not perfect, our result is a significant improvement over the original low-resolution video.
Watanabe et al. Also process this type of hybrid data to produce a high-resolution video. They use motion estimation followed by DCT-based frequency spectrum fusion. Their approach causes artifacts such as blocking, ringing, and spatiotemporal incoherence.
When optical flow is accurate, as in this example, our approach produces a near-perfect reconstruction despite the facial expressions and cloth deformations. Our system enables users to not only produce better videos, but also better photographs. Capturing the best instant in time can often be a difficult task, and users may often miss the key moment, especially when the subject is unpredictable. The cameras of the future will automatically capture a low-resolution video along with the user's desired images. Using our framework, users can, after the fact, roll back in time and select the high-resolution photograph they wish they had captured. Our approach enables not only spatial resolution enhancement, but also temporal resolution enhancement. In this example, occlusions and fast motion make for a particularly challenging case for optical flow algorithms. Although our result includes some artifacts, our system is able to generate plausible intermediate frames and create a video that is 8 times slower. We can combine the temporal and spatial steps of our approach to produce spatiotemporally enhanced videos. We start with this low-resolution video and enhance it spatially. Notice the detail in the magazine pages and her dress. We can also increase the temporal resolution to produce a spatiotemporally enhanced video. Increased temporal resolution enables dynamic retiming effects. For example, we can easily reverse time and create unusual clips. To perform this retiming, we have built a simple curve interface that allows the user to choose the timing of the different portions of the segment. Our system takes the interface output and produces the retimed results by smoothly varying the timing. This enables emphasis of specific parts of a video. In this example, we focus on the interaction between the ball and the player. We can put more emphasis on their contact through retiming.
In addition to simulating hybrid data, we also capture data using a camcorder and a digital SLR placed close together. The SLR captured stills at 6 megapixel resolution at 3 frames per second, while the camcorder captured video at 720 by 405 resolution at 30 frames per second. We zoomed into part of the video to compare the resolution improvement. Our system improves the video and recovers high-frequency details. In conclusion, we present a framework for enhancing spatial and temporal video resolution by hybrid video and still imagery. Our framework enables a variety of applications, including enhancing video spatial, temporal, and spatiotemporal resolution, shifting a still frame in time, and retiming videos for artistic effects.